Welcome everybody. In today's class we will be learning about Bayes theorem. It is an important theorem in statistics. In fact, I would say it is a very important theorem, and it is imperative that we understand the Bayes theorem. Now, before we could head on to learning about the Bayes theorem, it is imperative that we understand the following terms. We need to know what is an dependent event, an independent event, and conditional event. Probably you can use the term probability in all of these cases. So in this case I would be interested in the probability, the conditional probability, the probability associated with an independent event, and the probability associated with the dependent event. So that is my main focus here. Now let me give you a illustration for dependent event, the probability associated. The dependent event. Now suppose you take a box, and in the box you have 3 black marbles and you have 2, say I'm going to take this as blue marbles. Blue marbles, and these are all black marbles. So I'll write black over here. Now let A be the associated event of drawing a blue marble. In particular, I want to represent A to be the event of drawing the first blue marble. So that would mean we are interested in drawing both the blue marbles. So the idea here is I would like to study the probability of drawing both the blue marbles in a row. Okay, so that means A is the event of drawing the first blue marble, and let B be the event of drawing the second blue marble. So now what I'm interested is, as I mentioned to you, we are interested in getting the probability of drawing both the blue marbles, but we will do it consecutively, right? One after the other. So when I say we are interested in studying the probability of drawing both the marbles in a row, it means one after the other. So that is how we are going to be drawing. So as I mentioned to you, we have 1, 2, 3, 4, 5 marbles in all, and there are 2 blue marbles and 3 black marbles. So there are 2 blue and 3 black. Now I'm interested in knowing the probability of drawing the first black marble. So what is this? This is nothing but drawing the first I would say blue marble, right? So what is the exhaustive case? Totally you got 5. What is the favorable case? You got 2. Now the box has got 3 black marbles and 1 blue marble. This is the updated scenario. So now I'm interested in knowing the probability of B given that A has occurred. So how do we say I want to know the probability of drawing the second blue marble given that the first blue marble has already been drawn, right? So what is this? This is nothing but B, given that A has already occurred. So how are we going to find that? So this is nothing but totally how many marbles are there? 4. And what is our favorable case here? Our favorable case here is going to be just 1 here, right? So place that 1 there. And to sum up, right, what is the conclusion? The conclusion is, what are we interested in? Therefore, the probability of both the events happening so what it means, first A and then B. So the first blue marble is drawn, and then subsequently the next blue marble is drawn. So what is the probability of both the events happening? For the first one we got 2/5, second one we got 1/4. So the answer is 2/20, which is equal to 1/10. So that is the answer for this illustration. So this illustration I gave to explain to you the concept of dependent event. So in writing, we can write it like this. So this is equal to 1/10. What is this? This is nothing but probability of A into probability of B occurring, given that A has occurred. Okay, now coming to independent events. Now on one hand, you got a fair die. Okay, so die means, or you can say dice or dice, die, whatever you want you can say. That means it has got a label from 1 to up to 6. And then I got a fair coin. Fair coin has got a head on one side and a tail on the other side. Now the question is, I'm interested in finding the probability of getting a head when the coin is tossed and getting the number 3 when the die is tossed or dice is tossed. You follow me? On one hand you have the dice and on the other hand you have the coin. So you're basically performing the experiment concurrently. Now my question is, are they dependent or independent? They are independent. The occurrence of a head will not hinder the occurrence of the number 3. So if I were to take A to be the head turning up and B to be the number 3 turning up, so the probability of A, what is it? We got exhaustive case 2, it's 1/2, and the probability of B, how many numbers are there? We got 6, and the favorable case, what is the favorable possibility of getting the number, or I would say of obtaining 3? What do you think? How many 3s are there in the die? If you were to take the dice, how many faces are labeled as 3? We got 6 faces. In 6 faces, there's only one face which has got the label 3. So the probability of 3 turning up is 1/6. Now, as I mentioned to you, we are interested in 2 events happening concurrently. So therefore, the probability of both occurring is equal to probability of A multiplied with probability of B, which is 1/2, multiplied with 1/6, which is 1/12. So this is the solution. Okay, now I have to explain you about conditional probability. So we have finished dependent event, or probability associated with the dependent event, probability associated with the independent event. Now we need to find out the probability associated with the conditional event. So we call it as conditional probability. So what illustration are we going to see here? Okay, let me give you this beautiful illustration. Imagine you have, I hope you are able to see this, you have a class of 30 students. Out of 30, say 18 students play, let me take it as basketball, and 12 students play football. Now 5 students play both. So the class has got 30. Now we are saying that 18 students play basketball, 12 students are playing football, and we are also saying that 5 students play both. The most important question here is 18 plus 12 is 30, but where is the 5 going to be accommodated? So that would mean the 5 is present inside the students playing basketball and students playing football, right? So there are 5 people who are actually distributed here. So now the question, all important question comes is it possible for us to get the probability of a student playing basketball given that the student also plays football, right? So let me frame the question in the following manner. So what I'm going to do is, as I mentioned to you, I'm going to be taking A to be the students playing basketball. So let me just take or write that down here. Students playing basketball, and we've been given 18 students. If I were to find the probability for A, probability of A is going to be 18 divided by 30. So this would mean if I were to reduce this, 3 would divide this 6 times, 3 would divide this 10 times, 2 will divide 3 times, 2 will divide here 5 times. So you have 3 over 5. So meaning is, if you pick a student from the class of 30, the probability that the student will play basketball is 3 over 5. Now let B be the event associated, or you can say students playing football, and that is given to be as 12. Now we are also given that 5 students play both basketball and football. So that would mean A intersecting B is given to be as 5. So that means, let me write that down here. Students playing basketball and football. So the probability of picking a student would be 5 divided by 30, which is equal to 1 over 6. Now we are interested, given that the probability of student playing basketball, can we get the probability of student playing football? You follow me? So we are interested in finding the probability of student playing football given that A has already occurred. So probability of B given A is nothing but probability of, you can write this as B intersection A divided by probability of A. This is what is going to be very important. Probability of A intersection B is equal to probability of B intersection A from the theory, and we can extend it to probability. So this concept is what is going to be utilized in Bayes theorem. So probability of B intersection A or A intersection B is equal to 1 over 6 divided by probability of A, that's 3 over 5. So this is 1 over 6 multiplied with 5 over 3, and that would mean 5 over 18. Let me take this as 1. Now what if it is the other way? What if I am interested in finding the probability of A given that B has occurred? How would that be? in that case, this is going to be probability of A intersecting B divided by probability of B. So I'm interested in finding the probability of a student playing basketball given the probability of the student playing football. So this is already given. Now if I were to take this as 2, I can very well write it like this, right? P of A given B is equal to P of A intersection B divided by P of B. This is always possible, right? Now from 1 I can rewrite this as P of B given A multiplied with P of A is equal to P of B intersecting A. And from 2 I can write P of A given B times P of B is equal to P of A intersecting B. So since P of A intersecting B is same as P of B intersecting A, I can equate these two things. So this would mean I have P of B given A times P of A is equal to P of A given B times P of B. Now from here I can write, this means P of A given B is equal to P of B given A multiplied with P of A divided by P of B. Right, I have just placed a parenthesis, in fact not needed, so I will just rewrite it one more time. P of B given A times P of A divided by P of B. Okay, now this P of A given B, this is called as posterior probability, and this is termed as likelihood. This is termed as marginal, and finally this is termed as prior. So this is what is called as the Bayes theorem, the most popular one.